Let's now take a look at a numerical example. Now, in all these lectures, we will be looking at numerical examples that are very small. The reason we look at small example is that we want to spell out almost every step of the computation, even though it might be just an addition or multiplication, because we want to avoid any symbol phobia on the minds of some students. Okay, there's nothing mysterious about the symbols. Once you see them in action with numerical values, then you may feel a lot more comfortable with the symbolic operation. But in order to show the numerical addition multiplication within a slide or a page of the textbook, we have to stick to small dimensions. Now, in many cases, that actually does not capture a key difficulty in the challenge. That is the challenge of scale. Okay, so we would not be able to demonstrate why the problem is difficult because it has to scale up. Now, in this case, it turns out that usually the scale of a single cell is not that great. Okay, but still, we're talking about, in this case, a 4-user cell, which is a lot smaller than any typical cellular traffic that you can expect. Now, having said that, the advantage of small examples is that we can write out every step in the textbook or during the lecture. So here is the Gij values captured in a 4x4 tables. Okay, there are 4 users. And we're going to make up some number that will make our computation very easy. We say the diagonal entries, which are the G11s, G22, G233, and G44, they're all the same, which is 1. Okay? And then the Gijs are smaller because of the help of spreading code for the GIIs. And G12 in general may not be equal to G21. Okay, so this is G12, this is G21. All right, now these are the given parameters depicting the channel conditions for both the direct channels and the interference channels. Now, what about the target gammas? I'm going to say that gamma 1 is 2, gamma 2 is 2.5, gamma 3 is 1.5, and gamma 4 is 2. It turns out this set of gamma target SIRs is indeed achievable. And remember, the gammas are unitless numbers because it's the ratio. And then the noise levels, the NIs, are all equal to 0.1 in the units of milliwatts. So that's the set of constants. And now let's take a look at what would happen to the transmit power vector over discrete time slots from initialization at time 0 forward. Now, of course, in a real system, there's mobility. So you don't even have the same constant number of users. In a real system, the channel may also change before your algorithm can converge. We're skipping those important details in practice just to focus on a simple example to illustrate the dynamics of convergence of the p-vector. Now we start with an initialization or a time 0. Let's say we initialize all the power levels to be 1 milliwatt. Okay, now let's calculate what is the corresponding SIRs. The SIR for the first transceiver pair at time 0 initialization is simply 1 times let's see, this is 1, okay? It's 1 times 1.0 milliwatt. Okay. Then we'll write down the similar expression for the interference. Let's say, what are the interference channels? Well, we got 0.1 from the second transmitter, 0.2 from the third, and 0.3 as the interference channel gain from the fourth user. So we have to multiply 0.1 by the transmit power for the second user, which is 1.0. And then 0.2 times, again, 1.0, because everybody's power is initialized to be 1 milliwatt. And then 0.3 times 1.0. plus don't forget a little noise term, 0.1, and this turns out to be 1.43. Similarly, we can calculate the SIR for the second user at initialization, which turns out to be 2. For the third one, which turns out to be 2 as well, and the fourth one, which turns out to be 2.5. Okay, if you look at these numbers, these four numbers at initialization, and compare with the target SIRs, okay, you see that the first user is not getting to the target SIR. Neither is second user. Okay. But the third and the fourth user are actually getting above their target SIRs. Instead of 1.5, you're getting 2 already. Instead of 2, you're getting 2.5. So what would you expect? Intuitively and mathematically, you expect that at the next time iteration, number 1, you will see that the first and second user's transmit power should go up, and the third and fourth user's transmit powers should go down. And that is exactly the kind of negative feedback that we will see. Okay. Well, let's look at the kind of powers that we'll be looking at. P1, okay, now at iteration 1, is gamma 1 over the SIR just observed times the power, okay, at the last iteration. And this equals 2, your target, over 1.43, what you're currently getting, multiply your current power level, 1.0, and that is 1.4. Okay, indeed, now you're going to blast more power than before, okay, because you were not achieving your target SIR. Similarly, the second user's transmit power now becomes 1.25 instead of 1. Whereas the third and the fourth user's transmit power, you can easily verify the calculation, are actually smaller than the last round. They are 0.75 and 0.80 milliwatts respectively. Everything is in milliwatt for the power unit. Okay. And that confirms our intuition. Okay. If you overshoot your target SIR, lower your power, otherwise increase your power. Now, what happens to the SIR now? The SIR at this new iteration now becomes the following. Okay. Again, direct channel gain is 1, multiply the new power, which is 1.40, divided by the interference channel gain 0.1 times the new power 1.25 plus direct interference channel gain 0.2 times the new power 0.75 times plus 0.3 the interference channel gain multiplied by the new transmit power 0.8. This is the interference plus the noise, and you get 2.28. Okay. Now notice 2.28 here now is both bigger than the last round SIR, which is 1.43 if you remember, as well as bigger than the target SIR2. So not only you enhance your SIR, you enhanced a little too much. You overshot for the first user after this round. So what would you expect to happen in the next round? You expect the power for the first user will now go down. Okay, so power go up, power go down, and you hope that this oscillation will dampen and eventually converge. Let's finish this calculation. Okay, so the second user at iteration 1, the SIR is 2.34, okay, which is bigger than the SR at the last iteration, which was 2, but not big enough yet. The target is 2.5. So expect that next round, the power for the second transceiver pair will still go up. In the SIR3 at this iteration is 1.28, SIR4 at this iteration equals 1.82. And both of these are not quite their target SIR. So what you see after one iteration is that the first user actually overshot. Okay. The second user didn't overshoot. The third and fourth user actually now they're dipping below the target SIR now. And next round their power should increase. All right, so now you can go through this yourself. I'll look at the textbook and I'm going to just show you the cooked product. In the end, we can plot these transmit power values in milliwatts over the iterations. We just went through one iteration. You can keep going and then you see the ups and down quickly saturates, and around iteration 15 you pretty much converge. Now we will not have time to rigorously talk about so-called exit condition of an iterative algorithm. Okay, when should you converge to have a guaranteed error bound? We'll just hand-wavy way say that if the transmit powers no longer vary a whole lot from one iteration to the next, we call that a convergence. And this induces, of course, a convergence in the target SIR towards the target SIR over these iterations. In fact, around iteration 10 for sure, the SIRs converged, and as you can see, they achieve their target SIRs, 2.5, 2, 2, and 1.5 respectively. This actually is a very fast convergence. Within basically a few iterations, we achieve the target SIR. Now everything we have talked about so far, okay, the formulation, the optimization view, the game view, the numerical example, are all about what people call the inner loop power control, which says you have a target gamma feed into you and you have the current SIR measured, and this is going to update your transmit power. There's actually another loop, the outer loop, which operates at a slower time scale. Okay, by picking a certain transmit power through the effect of wireless network interference, you're going to observe at the receiver a certain error rate. Okay. And this error rate is an artifact of the kind of gamma that you pick. And the outer loop control says, you know what, is this too much error? If so, you should increase gamma. If not, maybe you can decrease gamma. So now in the outer loop, gamma is an output, not input. Gamma is a variable, not a constant. Now we will not have time to talk about it, but in 3G and 4G networks, clearly for data-centric applications, you can't just have a target gamma. Everybody wants a bigger gamma. The bigger the gamma, the higher the data rate, or correspondingly, the lower the error rate. So now you have to balance different users' demand for a bigger gamma. You know you can't give a big gamma to everyone. Then what would be an efficient and fair allocation of gamma? That is something that is very interesting. We just are running out of time. But before we close this lecture, I want to highlight in practice how is transmit power control used. Now we assumed that everybody has the same clock. Of course, in reality, you have asynchronous system. The clocks at different mobile stations run slightly different. And the transmit power levels cannot be just any real number. They can only jump in a discrete way. For example, the granularities might be 0.1 dB, 0.2, or 0.5 dB, depending on which cellular protocol you are talking about. But if you look at an asynchronous and discrete power level version of DPC that is actually implemented in virtually all the 2.5G and 3G networks, and depending on the protocol, the frequency of running the inner loop could be anywhere between 800 to 1500 hertz. Okay. So every second, roughly speaking, this calculation of DPC is run 1,000 times. Now you can count how many 3G and 2.5G devices are out there, and you see that this algorithm is used with an incredible number of times every single day out there. And indeed, transmit power control together with what's called soft handoff is what made all the 3G standards work. So not only is this DPC an elegant mathematical entity, it is also a practically extremely influential and useful artifact. So you may wonder, how can I make cellular speed run even faster? We'll come to some of these ideas, from splitting the cells, overlaying with smaller cells, to using multiple antennas and dividing the frequency bands more refinedly later in the course. Well, every lecture will conclude with a summary slide. And in today's summary slide, we want to highlight two things that we learned in this very first lecture of the course. One is that different users' signals interfere with each other in the air. And that happens in all wireless communication. In the cellular world, we use transmit power control to manage this interference, to mitigate the impact of this negative externality. In particular, we saw the picture of a feasible SIR region, the trade-off, with a Pareto optimal boundary. And we saw the cocktail party analogy. In this case, we're controlling the volume of all those that talk during this cocktail party. We also saw a specific mathematical formula. It's called interference coordination with distributed power control, a DPC. And the conceptual highlight is that there is a negative feedback, and the feedback is all captured in the current SRR value. You just compare that with your target fixed gamma and use that ratio to adjust your power level up or down accordingly in the next time slot. And we saw that this can be viewed as a distributed solution to an optimization problem, which turns out to be a linear programming. Or we can model that as actions by intelligent agent in a non-cooperative game that models the competition due to interference. Both the conceptual points of interference, tragedy of common, negative externality, as well as the mathematical language, such as what defines optimization problem and what defines a game, will be so frequently used over and over again in the rest of this course. And indeed, in the next lecture, we will shift gear from the world of CDMA over to the world of online ad auction. How does Google sell the advertising slots on a search result page? We will see how the ideas we talked about in a game can be applied to analyze the mechanisms that Google uses. So see you at the next lecture.